This week we're going to study inverse matrices, and what inverse matrices do is give us an efficient way of solving some systems of equations. And so this adds to our toolbox as far as how we can approach systems of equations. So far we know we can graph them, we can use some type of algebraic manipulation like elimination, or we can use augmented matrix. And so this will simply add to those tools and those approaches we could use. Now, to define the idea of a matrix, inverse matrix, an inverse matrix is one where we multiply the original matrix and we end up with the identity. And actually, the multiplication for these is commutative, although you don't have to check that when you're verifying inverses. Not all matrices have an inverse. In fact, at the very least, you have to be a square matrix, and then you may have an inverse. Even if you're a square matrix, you might not have an inverse. And so this will come up when you're trying to find an inverse through the row operations. And we'll use the notation where you use an exponent of -1, but what that will actually represent is the inverse matrix. And so one way to think about what we're going to do here is that we're going to have a matrix A, and we're going to use something to see if it has, do we have an A inverse like this? And can we say, once we have that, that the following is true? This would have to be true if it is, in fact, an inverse. And so if this is n by n, this will also be n by n, and the identity will be n by n as well. And so the identity matrix is that matrix that has ones along the diagonal and zeros everywhere else. It essentially acts like a 1 when you're multiplying. Now, to verify two matrices are inverses, you need to make sure that when you multiply them, you do in fact get the identity. And this is really just a check that you understand what's going on. And so if I was to multiply these two, so if we were to just get rid of this and make it multiplication, then remember rows hit columns, so I'd multiply this times this. I'd get, let's see, for the first entry, I would get 3 times 3 is 9, and then plus a -8, so I'd get 1. That's looking good so far. Next entry, I get 3 times 4 is 12, minus 12, so I get 0. Here I get -2 times 3, so -6 plus 6, 0. And -8 plus 9, 1. So these are, in fact, inverses. And you may say, well, hold on a second. You said that what we need to do is check that AB equals BA equals I. And so, well, once one of these is true, so this is true, but once one of these is true, the other one automatically is because of the properties of inverses. So you really only have to check one direction of the multiplication. If only one of these values doesn't end up looking like an identity, so if this was a -1, a 3, or anything like that, I would say they're not inverses. So let's take a look at the next one. I'm going to multiply, so I'm going to ignore that comma there, and I'm going to say, okay, I got, for my first entry, 2 times 1 is 2. 2 times -1 is -2, so I get 0 here. And now whatever this is, I don't really care. These are not inverses, because I needed a 1 there to even have a chance of them being an inverse of each other. So again, when I'm multiplying these two, I'm looking for that property, and the other property, the commutative property, automatically holds. But I'm not sure if this really shows the usefulness. This is more checking the definition. So what is the usefulness, and how will we find this inverse? Well, again, the usefulness comes down to being able to solve systems of equations. But really, we got to be able to find an inverse first. And so what kind of tricks can we use? Well, based on the idea that if I'm trying to multiply some matrix, and it doesn't really matter what it is, so A, B, C, D, I'm trying to find something else I can multiply it by. So I could say maybe E, F, G, H. And what I want to have happen is 1, 0, 0, 1. So this is in the 2 by 2 matrix case, right? Well, if I do this, I can actually write a system of equations. And so if this is my matrix A, and I'm hoping this is A inverse, I can end up writing a system of equations that will actually solve what comes out of this and will give me an inverse if it has a solution. But there's an easier way to actually do that. And anytime I have a system of equations, one easy way to find a solution would be to use an augmented matrix. And so actually you end up with a really nice trick. The trick is, what I do is I take A and I augment it with identity. And then I'm going to row reduce this. And so it's kind of like solving the system of equations if I was to multiply this out and work with it. I row reduce it, and what I end up getting is the identity on the left, if it has an inverse, and A inverse on the right of my augment. So this is a really easy process, well, about as easy as row operations can be. So mostly easy, but sometimes a little complicated. And it will give me the inverse. And if there's not an inverse, we'll get something like a row of zeros that makes you think 0 equals 1, or something else that can't be true. So let's see how this works with an example. So I give you a matrix A. In this example, I can tell you right now, we do have an inverse. And so remember what the process is. I'm going to take A, and I'm going to augment it with the identity. And so whatever size A is, the identity will be the same size, so that particular identity. So here what I'll do is, to find this, I'll say, okay, I'm going to make a huge matrix. So 1, minus 1, 1, 0, 2, minus 1, 2, 3, 0. And I'm going to augment this with the identity. So 1, 0, 0, 0, 1, 0, and 0, 0, 1. And now my goal is to start row reducing, and I want this side to look like the identity. So, okay, so I'm going to go through the usual steps with that. I say, okay, I got 1 and 1 here. We got a 1 there. I need a 0 here and here. Well, this one's taken care of. This one isn't. So what I need to do is minus 2 row 1 right here. So you can tell right now I'm doing the same thing we did last week. All right, so everything else is staying the same. So I got a little bit of copying down to do. And then I want to do that last row operation. Remember, you don't have to copy down the augment each time. Just remember where it is for the end. 0. And okay, now I know I'm going to get 0 here. Then we got minus 2 times minus 1. We got positive 2. And 3 is 5. And then we got minus 2 times 1 is negative 2. And 0 leaves me a negative 2. So I go, okay, we got that. And then I still am doing the row operation over here. So actually, it's going to be a minus 2 times 1 and a 0. I'm going to get a minus 2 here. And that's how, and then a 0, 1 because of those zeros. This is actually how our inverse is going to develop by right here. Okay, so my next step, I need a 1 here. So I'm going to multiply by 1/2. I don't want to add or subtract to get that 1, right? Because then I'll mess up the zeros I just made. So if I do this, everything stays the same. 1 minus 1, 1, 1, 0, 0. But now right here, I'm going to have 0. I'm going to have 1. I'm going to have minus 1/2. I'm going to have 0. I'm going to have 1/2. And I'm going to have 0. You know, it's not fun when fractions pop in the mix, only because we have to be a little more careful. But remember that overall, it didn't make it more difficult. It's just more to keep track of. Now that I have that 1, I want to get rid of the minus 1 above it and the 5 below it. So to do that, what I can do is add row 2 here and subtract 5 times row 2 here. Okay, so if I do this, then I end up with 1, 0. 1 minus 1/2 is 1/2. 1, 1/2, and 0. Okay, and the middle row doesn't change. 0, 1, minus 1/2, 0, 1/2, and 0. And then for this next one, I got 0, 0. That's what I want to have happen. And now I got to be pretty careful here, so I might write down a little bit of scratch work as I'm doing this. I want to take minus 5 times this 1 and add it to that 5. I already did that, right? I got 0. But now I want to take minus 5 times the minus 1/2. So this is my scratch work. Minus 5 times minus 1/2. And then I want to add it to negative 2. I just don't want to go doing that in my head. So I end up with positive 5/2 minus 2, which is 5/2 minus 4 over 2. So what do I end up with after all that? I just get 1/2. Okay, so that's actually 1/2 down here. And that's the beauty of a calculator. So obviously if you had a calculator, that'd go much quicker. And now this is going to be a negative 2. Nothing changes. Minus 5 times 1/2 is minus 5/2 and 0. That doesn't change. And then we get our 1. Okay, so finally what I need to do is I need to make this a 1, and I need to get rid of this and this. However, I see a little bit of a trick here. If I make this a 1, I'm going to have to be multiplying by halves all the time, right? But what if I use this 1/2 to get rid of this and this? Wouldn't that make life easier first? So that's what I'm going to do. I'm going to say, okay, you know what? Let's just take care of this right now. Let's go ahead and add row 3. And let's go ahead and subtract row 3. And then I'll make everything a 1, because since all of them are in the same denominator, it'll make things way easier. So for this top row, the 1 and 0 won't change because of the 2 zeros in row 3. And I'm subtracting 1/2, so I get a 0. And now I have 1 minus a negative 2. I got 3. And I got 1/2 minus a negative 5/2. So I got 1/2 plus 5/2. That's 6/2, which is also 3. And then I got 0 minus 1. So I got a minus 1. Okay, for my next row, I got 0, I got 1. 1/2 and negative 1/2, I got 0. Okay, the negative 2 just comes up. Now I got 1/2 minus 5/2. So that's negative 4/2. that would be a negative 2. And then I got my 1, and I got 0, 0, 1 half, minus 2, minus 5 halves, and 1. All I got to do is one more step. I need this to be that 1, so I can multiply everything by 2. And then finally, I get my last matrix. I get 1, 0, 0, 3, 3, minus 1. I get 0, 1, 0, minus 2, 1. And then finally, 0, 0, 1, minus 4. And this right here, so if I multiply by 2, the fraction's gone, right? So I get minus 5 and 2. Okay, let's remember where our augment is. So all that work, I wouldn't say, like I said, it's not hard. We're just adding and multiplying. It was just a little bit to keep track of. This right here ends up being your A inverse. We got identity and A inverse. Now, you don't want to just circle this. That's kind of lazy. So what I'll do is I'll write it right here, somewhere where I can find it. So A inverse equals 3, 3, minus 1, minus 2, 1, and minus 4, minus 5, 2. So again, finding the inverse is just a matter of row operations and knowing which row operations to use. And you can always double check your work, because when you multiply this matrix times A, you should end up with the identity, right? So you can double check that this is the correct one. I promise you I already double checked. And so this is the correct answer. Now again, what's the point? Okay, you found the inverse matrix and you multiply by A, you get the identity. So does it really matter, I think, is a fair question. So what can we do with this once we find it? Well, let's think about a system of equations, right? So anytime I have a system of equations, we already know that I can think of it as an augmented matrix, right? So I could take A and I can put some kind of values here. Now, what is this? What is this A? What is this B? This would be the coefficient matrix. And this would be a matrix of the constants. I don't know if you ever thought about it that way, but that's essentially what we do. We make an augmented matrix. So if I had, for example, 3x plus y equals 5, 2x minus 1 equals 2, something like that, right? The coefficient matrix goes right here. It's 3, 1, 2, minus 1. And then we augment it with the 5, 2, right? So this is one way to solve a system. Another way would actually be to think of this system as a matrix equation, and AX equals B. In this case up here, the matrix equation would be AX equals B, where A is just the coefficient matrix, 3, 1, 2, minus 1. X is the matrix of the variables, which here are x, y. For us, it'd usually be x1, x2, x3, etc. And then B is the 5, 2. Okay, now think about this for a second. What if your matrix A is invertible? Well, in other words, it has an inverse. That means I can multiply on the left on both sides, and something pretty cool will happen. So I do that, and then what happens over here? What's A inverse times A? It's the identity. And the identity times any matrix will be the original matrix itself. So I end up with I times X, but that's just X. So I actually find the solution. It says right here, find the solution by multiplying A inverse times B. So in other words, if I had the inverse of this, I could just multiply it by the column 5, 2, and I would actually have the solution. And you could change this 5, 2 to anything, and I could still find the solution the same way. Computationally, this is very, very nice. So this gives me another way to solve a system of equations. And I can actually show you this. Now, first thing I'm going to do is actually write this as an augmented matrix, right? So as an augmented matrix, this system would look like this. 1, minus 1, 1, 2, oh, hold on, that's a 0, right? Because there's no x1. 0, 2, minus 1, and then 2, 3, and there's no x3, so a 0. And then we got 10, 4, 5. So this is augmented matrix, the augmented matrix. Well, what about as a matrix equation? Well, I'd say we got 1, minus 1, 1, just the coefficient matrix, 0, 2, minus 1, 2, 3, 0. And then our variables, x1, x2, x3. And then this equals B, which would be the constants 10, 4, 5. This is the matrix equation. All right, so the question is, how can I solve this? How can I get x1, x2, x3 equals and then something being the answer, right? Well, from the process we just said, if we know A inverse, all we have to do is multiply A inverse times this. So do we know A inverse? You should recognize this matrix. We just worked with it a second ago. And actually, I know from the previous example, A inverse, if this is A, is equal to 3, 3 minus 1, minus 2, 1, and minus 4, minus 5, 2. Now, if I didn't have this, I'd have to find A inverse, right? Obviously, if this was something I was giving you, I would have you maybe find A inverse as part A and then use A inverse in part B. But of course, here we conveniently already found this value. Okay, so now how do we actually solve this system of equations? Well, based on the previous rule, I can say x1, x2, x3 equals this A inverse times matrix B, 10, 4, 5. Okay, and this is quick multiplication, right? This is something that you can do based on the last section. And so I'll go ahead and do it and tell you what I get. I end up with 47 minus 33 and minus 70. So in other words, my solution is x1 equals 47, x2 equals minus 33, and x3 equals minus 70. And now if I was to change these, 2, 2, 2, all I would do is change these right here as well, 2, 2, 2, and we get the other answers. As long as this part stays the same, you can continue solving by just multiplying. So once you find A inverse, you can solve any system with those particular coefficients, and that's the power behind this. So as you're studying this, you should be able to find the inverse given a matrix and double check that it works. You should be able to take any system of equations, write it as an augmented matrix, but also write it as a matrix equation and use that inverse to solve it.